Welcome to Calculus. Today we will investigate integration by substitution, taking a look at polynomial and rational integrands. We'll take a look at three examples. Our first example is the integration of 1 plus 6x all raised to the power of 4 times 6 dx. So what we have to recognize when we're looking at an integrand like this one is that it's really based upon the chain rule from differentiation. So to help us see the connection here, let's remember what the chain rule says from differentiation. So it claims that if I've got a composite function, f of g of x, and if I take the derivative of it, that's equivalent to the derivative of the original function. In fact, let me clean up my notation here. Let's say d dx. So that's equivalent to the derivative of the outer function f of x without changing the inner function g of x times the derivative of the g function. So that's differentiation. What we're faced with is, how do I really accomplish the reverse? How do I integrate a composite function back to its original composite function? In other words, it's antiderivative composite. So that's what we've got. It's really antidifferentiation of composite functions. And we'll state it right below here, since it is a result that follows from the chain rule for differentiation. So here's antidifferentiation of composite functions. So let's state it, and then we'll use it here for this example number one. So this is really the reverse of the chain rule, antidifferentiation of composite function. And it says that if I'm taking the integral of f of g of x times the derivative of g, so that's really starting with this right side, and if I'm taking the integral, it gives me back the antiderivative, which we'll denote by capital F, of g of x plus c. And again, we include that c as the constant of integration because we're dealing with indefinite integrals here. Well, let's put this into use with this question here. So I've got the integration of, again, 1 plus 6x to the fourth times 6 dx. What I want to do first is identify what is equivalent to my g of x. And then what I need to ensure is that I have an expression that will stand for the derivative of g. So I'm going to note that my g of x function is this linear 1 plus 6x. So out here on the side, I'm just going to identify that as my inner composed function g of x. And I want to take its derivative. I want to think, what should I include in that integral so that I can use this antidifferentiation of composite functions? So the derivative of 1 plus 6x is going to be just 6. And that matches exactly with the multiplier that I've got there. So this one's actually set up for immediate application of this antidifferentiation technique. So I'm ready to integrate. And so really what I need to do is I want to find the antiderivative of this outer function, which is essentially x to the power of 4. I'm simplifying because my x here is the other function, g of x, 1 plus 6x. But in general, if that's x to the power of 4, its antiderivative is going to be 1 over 5 times the inner function to the power of 5. Now, by the rule, that function is just plain g of x. So all I've got to write in here is 1 plus 6x. And the last thing that I need to include is the constant of integration plus c. And that's really complete. This example is very quick. Now I do want to check the result by differentiation. So if I were to take the derivative of this answer that I got, I would bring, so I got to apply the chain rule. I'd bring that power 5 down as a coefficient. So a fifth times 5. In fact, we'll write it down here below. And then I'm going to have my inner function 1 plus 6x to the power of 5 minus 1. And then I need to take the derivative of the composed function, 1 plus 6x. Its derivative is 6. And I'm just needing to check, does this match my original integrand? So 1/5 times 5 cancels. And this expression matches exactly what I had in the original integral. And so it checks out. Let's take a look at a second example that involves a square root. Here I've got the integration of t times the square root of t squared plus 2 dt. The first thing I want to do is rewrite the square root as a power of 1/2. So this is the integral of t times t squared plus 2 to the power of half dt. Again, I want to identify what's my inner function. If I put that rule again for antidifferentiation of a composite function, it says the integral of f of g of x times the derivative of g of x dx equals the antiderivative at g of x plus c. So as always, what's very crucial for me to identify is what's my g of x, and then I need to confirm, do I have other factors in the integrand that would constitute my derivative of g of x. So in this function, my g of x, the composed inner function is t squared plus 2. So I'm going to just make a note here on the side. G of x is t squared. In fact, I should call it g of t, just to match my variables, is t squared plus 2. So I just want to take the derivative and see, do I have the factors to constitute the derivative of g of t? So that's going to be 2t. And what I see is that I have part of what I need, but part of what I still need is missing. I have the t, but what I'm lacking is the constant multiplier 2. Now, what we can do is create for ourselves that multiplier. So what I'm going to do is rewrite the integral. I'm going to put 2t, since that's what I need, but I need to be faithful to the original and not just include multipliers. So I'm also going to multiply by half. So the total product there is going to be 1, but I have a 2 there that I can use for the anti-differentiation of a composite function. So I'm going to fill in the rest. The other factors here in the integrand are not changed, so I'm just going to record them. And with this half that I really don't need in the integration, I'm going to let it pass to the left on the outside of the integration symbol. And when I do that, what I've got is now in perfect order in order to do the anti-differentiation. So now I've got that organization of f of g of x here with t squared plus 2 to the power of half, and then I've got the derivative of g, 2t. So I'm ready to integrate. This is now half times, so I need to integrate, find the antiderivative for this outer function, which is basically t to the power of half. So if I add 1 to half, that's going to be 3 halves, and I need to invert that for my coefficient, so that's 2/3. And then I'm going to put my base to the power of 3 halves, and then I need to just place t squared plus 2, that's the g function, plus c. I can clean that up by multiplying and reducing. So my 2's are going to cancel, and this ultimately is going to be a third times t squared plus 2 to the power of 3/2 plus c. And that's my integral for the second example here. Again, I should check it by differentiation. So if I were going to differentiate this answer that I just recorded, it would be a third times the power 3/2 become a coefficient times base t squared plus 2. Subtract 1 or 2 over 2 from 3/2, that's 1 over 2. And the derivative of the interior function, t squared plus 2, is going to be 2t. And then the derivative of c is 0. So again, I can reduce here. 3 divided by 3 cancels. 1/2 times this 2 cancels. And we're left with this expression that entirely matches my original integrand. So in our second example there, we did have to do some manipulation in order to come up with an expression that would match my derivative of the inner function g of t. Let's take a look at one last example that involves a rational function. So here I've got the integration of x over quantity 1 minus x squared cubed dx. Many times I want to rewrite these so that they're on the main level, some base to a power, instead of in the denominator in this case. So I'm going to rewrite this expression. It's going to be the integration of x times this base 1 minus x squared. And if I raise that up to the numerator, this power of positive 3 is going to become power of negative 3. So that lets me see if I can apply my anti-differentiation of composite functions rule. So I need to identify that g of x here is 1 minus x squared. So its derivative, which again I'm going to check to see if I've got it represented in the integrand, is negative 2x. So just like in the previous example, I have part of it. I've got the x, but the part I need is negative 2. So we have a strategy. I'm going to put the integration of, I'll put my negative 2, because I know I need it, negative 2 with that x out front. But then I know that this has to be an overall product of just 1. So I need to include the factor negative half. And just like we did in the previous example, I'm going to let that negative half pass to the left side of the integration. So my next step would be negative half times the integral of negative 2x times 1 minus x squared to the power of negative 3 dx. So now we're ready. We've got the correct pattern for our anti-differentiation. So this is going to be negative half times. So I need to take and find the antiderivative of this, basically x to the power of negative 3. So I'm thinking I'm adding to negative 3, 1, that's negative 2. I'm going to flip it over. So that's going to give me the factor negative 1/2. And then I'll put my power of negative 2. And then remember, I'm going to place my g of x function within that structure and add c. So all we need to do at this point is simplify. So negative half times negative half is 1/4 times, if I let this descend back into the denominator and let its power become positive, I'd have 1 over 1 minus x squared, quantity squared, plus c, and that would give me 1 over 4 times 1 minus x squared squared plus c. And that completes that example. We could differentiate at this point. Where I would go to do so is probably this step right here. So for that one, if I were going to differentiate, in fact, let me kind of make a version of it. Let's just go with 1/4 times 1 minus x squared to the power of -2 plus c. So again, just to check if I can get back to my integrand, I would subtract, let this power of -2 descend as a coefficient here. So that's going to become 1/4 times -2. And I'll place 1 minus x squared, subtract 1 from -2, that's -3. And then I need the derivative of 1 minus x squared, that's going to be -2x. And then the derivative of c is 0. And then to clean this up, my -2's are going to multiply to 4 and cancel with the quarter. And so we're left with x times 1 minus x squared to the power of -3. And that absolutely matches my original integrand. Thank you for joining for these 3 examples of taking the antiderivative or integrating composite functions. See you soon.